Good afternoon. Well, I'm at it again. I'm going to just start this video today, but it not necessarily mean it's going to go up. I removed the big long resistor that looked like somebody wound some wire on it. Well, it is a kind of like a wire wound resistor, and it measures about 9/10 of an ohm. 8 to 9/10 of an ohm right here. And here it is. No markings on it. It's mounted on some kind of a form, plastic form or something. And I thought it would be a high resistance. But there's no markings, and it reads 1 ohm, and it looks like it's probably made that way. I don't think anybody built it. However, somebody did add a little thin pigtail where my red lead is, where my red clip lead is, which made it very, very loose. So somebody had been working on this, and the resistor went from here, and this wire here goes to the center tap of the big transformer here, which I can give you a better look at. Now, they're not using the 5-volt winding for the 5U4. I don't know why, but they're not. Maybe because of the high voltage, the breakdown. Because this capacitor here, if you crank this all the way up, it's over 500 volts on this. I'm going to take this bracket off and see what the voltage rating is, but I'm sure it's not over 500. But there is a discharge capacitor in here. Now, I started drawing out a schematic, but it's kind of like, it's a mismatch. It's very hard to figure anything out here. There's a 47,000 ohm here, and this is the switch as you're looking at it right here. And the center tap of the high voltage transformer, red and yellow wire, goes to that long resistor that I just showed you. The primary of the power transformer goes to 2 terminals of the variac. So when you adjust the variac, you're adjusting the input voltage to the primary of the power transformer. That's how I was going to build my power supply. The third wire, the chassis isn't turned upside down right now, so I can't show you, goes to another location. I'm still in the process of tracing this out. This capacitor is that electrolytic. I put 500 volts on it because it's got to be rated at least that much. So I traced it down, and the switch, as you're looking at it from under the chassis, so far this is all I've got drawn out. The toggle switch, I'm going to have to turn this over to show you, works in reverse of any toggle switch that I have ever run into. When you turn the power off, the lever down, you're looking at under the chassis, and this would be sideways. In other words, you're looking at it as the chassis is turned upside down. These 3 terminals will be on the top, and these 3 terminals will be on the bottom. So when you flip the switch up to turn it on, most toggle switches would connect this and this, this and this. But no, it turns this and this and this and this. In other words, just the opposite. You flip the switch this way, it connects these 2. Flip the switch this way, it connects these 2. In other words, it works the opposite. So, okay, because that makes sense. Why the switch works that way, I don't know, but that would make sense because your primary is here. So this, I think, is a bleeder resistor, and I have not finished this yet, but the common negative is floating. It is not connected to the chassis. Goes down here to this terminal here, which are the two green wires that come here. Okay, so one of them goes to the 150,000 ohm resistor, and then they tie together at some point in the chassis, and they go to the 47,000, which I think is a bleeder resistor when you shut the thing off. So that's where I'm at right now. So I'm not going to worry about the neutral being fused, because the whole thing is going to work anyways, and that can be changed at a later date to the correct position. So we'll examine this here. It almost looks homemade, but it's got a coating on it, like a varnish or something. And no idea, but if that's 1 ohm, 8/10 of an ohm, and it stays cold, because it's obviously very low current, so it is not a dropping resistor for the high voltage. A lot of your power supplies would have a dropping resistor in there for your voltmeter, so you don't blow the meter out. But this is not on the voltmeter section, and it may not even have anything to do with that. But why it's so low resistance, I don't know, because I don't have a schematic on this. This is the back of the milliamp meter, and it was tied right here. It was soldered here, and it went to this terminal up here. And it was kind of a loose connection. Of course, the screw was loose too, like everything else here. But the connection was not soldered very good, so that has to be redone and probably put that back in. There's no point in putting a high wattage 1 ohm resistor in here, because this one here is running cold. So what I'm going to probably do, somebody put a wire on here already, a heavy lead, so I'll probably do the same and put one on here so that it'll be more stable, because it was just flopping around in there, and I'll do a better job putting it together. But as you can see, there's no markings on it. The readings that I'm getting on here are pretty close. This is the voltmeter over here, and it's pretty close, and I think the milliamp meter is working good too. In order to increase the current on this, the only way I can see in here would be maybe this 150,000 ohm resistor here, because the 47,000 apparently is a bleeder resistor, so that it discharges it when you throw this toggle switch here. So let's go under the chassis and let's go through some of this again. Alright, this is really a little bit hard to trace out. This is the 47,000 ohm resistor, and this wire here is the positive of that electrolytic that's on the other side of the chassis. This is the hot lead for that. Okay? You trace that up. Alright, I already traced all this out. This is the only way. Am I on camera? Probably not. This resistor is the only way I know to reduce the value of this by experimentation, because that's how I do things, to get more current. My concern is, am I going to damage that milliamp meter by doing that? There isn't a shunt resistor across the milliamp meter. There isn't. So this red wire, what I can see with my piss poor eyesight, goes to the lower end of this resistor. The other end of the resistor is a green wire, and if I traced it right, it goes down to the common point, which is over here to the common of this electrolytic. Okay? Now I put a voltmeter on here on the negative. This is the negative of the electrolytic that I showed you on the other side, 12 microfarad, and the positive is right here. This is the other lead. I put a voltmeter across it, and when I crank up the variac, I got 504 volts across it. So what I want to do right now is we're going to take the clamp off, and we got to loosen this nut here and take the clamp off so I can read the voltage rating of that electrolytic. As old as it is, it's holding 500 volts. It won't need to be replaced. I would like to reduce this fuse though, because when I showed on here on the PR57, zero to 1.5 amps, 175 watts max, it hardly moved the needle. And that was the current draw of this entire unit. So a 1 amp slow blow fuse will be put in here instead of the 3 amp that's in there now. I just have to dig one out of the box. But for now, we'll leave it. And another issue here, and I got a lot of figuring out to do here, because mainly my damn eyes. I don't want to mean to complain about it all the time, but, you know, I pretty well know what's going on. I just can't see to trace things out, as big as it is. Why they didn't use the 5 volt, this is the 5 volt winding from the filament transformer that's up there. They didn't use the 5 volt winding from the high voltage. This is the high voltage leads. This is your 5U4 socket. This is your high voltage. 400 volts from each leg to the center tap, which is right here. This is the center tap right there. However, there it goes in there. This grommet here is the wires for the filament transformer. So here is the 5 volts for the 5U4 comes from the filament transformer over to here. So that could be why they disabled it here. There's probably a reason why they did that, simply because of a breakdown voltage. You remember, we're putting out 400 volts on each side of the center tap. In other words, 800 volts from here to here, which I wouldn't try putting my meter on because I think it would go over the range of it. I don't want to damage it. I do have a meter that'll read the AC voltage higher, but I'm not going to risk ruining my fluke to do that. So I've got meters that will read that high. I think this will read 1,000 volts, and I'm not taking a chance. Usually they read higher on DC than AC, so not a problem. But the transformer is designed for that, but maybe they figure with this here that it may be better to have a separate filament transformer to run that. Regardless, there is a center tap here, because this grommet down here is for the filament transformer, and this one grommet here is for the power transformer, and there are only there's only one for the power transformer. This is the secondary, the 5 volts, and the center tap coming out of this hole. And if you look way over here, the other part of this filament transformer is over here, and I haven't gotten that far on my Rube Goldberg schematic. It's very complicated for me to draw it out. I start out on a small piece of paper, then I figure it out, and then I straighten it out. I give a lot of credit to the guys that make the schematics and draw them out on SAMs and all them, because stuff is all over the place, and wires would be crisscrossing and everything else, and it would be such a Rube Goldberg mess that I wouldn't even be able to figure it out myself. So what I do is I just want to get the high voltage area worked on to try to figure that out. So I'm going to try to experiment with that with clip leads and probably putting another resistor across to see if I can get some more current out of it. But what I got to do is find the circuit that the milliamp meter is in before I even attempt to do that. So the next thing I want to do here, and I know this video is is long and a lot of flapping, but however, I'm kind of showing you how I do things, how I trace things out, and it's not necessarily the way you would do it, because everybody that works on these things has a hell of a lot better eyesight than I have. So this apparently gets 115 volts or whatever's going in it, so it's a regular neon. I'm not too worried about that. It is not a over voltage light, warning light, or anything like that. It's simply a pilot light, and I haven't figured out how to get it out yet. There's nothing sticking out on here to get it out, and the only thing I tried to do was to pry it with a screwdriver, and that's probably what I'm going to have to do, but I'm not worried about that now. All right, let's get that electrolytic clamp off. I'll do that off camera, and then I'll show you what the voltage is on that cap. I'm curious. Wow, 700 working volts. That clamp I couldn't get off all the way because I think this end of the screw is stripped a little bit. I can tighten it up, but you can see that 700 volts, working volts, 12 microfarads. So that explains that, and I don't think we even need to bother taking that out. This is one of these things that is not going to get used all that much. Boy, I got a lot of, you can see how bent that is. I got a lot of straightening out to do on this. But anyways, all right, so we'll tighten that back up. As far as getting more current out of it, well, if you're going to power a radio, you want better filtering. So we can add another capacitor, but we're going to have to go two electrolytics in series with a balance resistor across each one. That is the way it is in the telemic. When I recap that, there's two electrolytics in series with 470,000 ohm resistors, one across each one. That's to keep the voltage equalized between the caps, so that one doesn't go too high and, get all the voltage and, So that is what I'm going to do on the power supply. But I got to trace out the milliamp meter. The voltmeter we're not worried about. What the voltage comes out, just reading the voltage. It's got obviously a shunt resistor inside. Anyways, so no doubt it has. Maybe the milliamp meter does too. But if we're pulling more current, if we can manage to get that to pull more, we can pull more current off of this, then we're going to have something to protect that meter. So I have to trace that circuit out. Well, the pilot light disintegrated. That's all it is a neon bulb, which I knew it was. But I wanted to remove it because I'm trying to trace out the wires. The yellow wire is one of the wires that comes off the milliamp meter, and there's a red wire that comes off the milliamp meter, and I haven't traced it out yet because this was in the way. I had to get it out of here anyways, so we're going to replace that, but we're not going to worry about that at this time because we still got the bezel in there. So a light could be shoved in there, or I might just take the bezel out. I would like a red light in there, but we'll worry about that later. So on this is the polarity reversing switch, which I want to be able to disable, but I gotta be careful because you got the way the reversing switches work is I get some light on here. You see the way they wired it, and that's how you wire a reversing switch with the crisscross wiring here. So, but we don't need to worry about that now as long as we don't reverse the polarity when we're working on the radio. We'll be okay. Otherwise, we're in big trouble. So, we connected up, we tightened up the electrolytic mounting here. So 700 wicking volts. I've never seen that, an electrolytic that high. I've seen 500 volt once, but never 700. Okay, so we're going to continue tracing it out. So this yellow wire here, my finger's pointing. Can't get this damn light to stay in the right place. Is one of the wires that comes off the meter, and I think there's another red wire down in here. We're going to do all that tracing off camera. So this is a challenge for me to trace out. Even though it's big and it's easy for me to work on, it's still a challenge. I give a lot of credit to anybody who could take and draw a schematic of this whole thing, because that's beyond me. I'm able to get some of it down on paper so I can figure out where I need to be to increase the current. You're getting, I haven't drawn the 5U4 yet in here, of course, obviously. But you're getting enough out of the 5U4. Your input filter, which is the only capacitor in here, is that 12 microfarad. This is going to be your DC. This is your filament. And on a 5U4, the filament and the cathode are one. So it's a directly heated cathode or filament. So from here to the common negative, not to the chassis, there is no connection to the chassis. You know, after looking at this on the video, the grounding here looks like something I would do because of my bad eyesight. See how sloppy that is? This cord, because of the original clamp ring they have here, that's why I suspect that's factory, but factory wouldn't do this. Maybe this unit came with a two-prong cord because the chassis is floating. So when you get the high voltage coming out of here, your high voltage comes out of these two terminals here, and if you got the polarity correct, this will be the negative and this will be the positive. But if you put a meter between here and the chassis, you get nothing, which is good. So that's a good thing. So this is a common negative, goes directly to the negative of the electrolytic, which is right here. And the positive's over there. All right, so I'm continuing with this. It's very boring and long, and if it gets too monotonous and it seems to be wearing thin, I'll just stop the videos and will not produce any more. Okay, the back of the milliamp meter, the red, we traced out, I believe it goes down over here. The red wire, I traced it out, goes here. And this is the center tap of the high voltage transformer. There it is right there. This is the front of the unit, of course, right here. This is the filament transformer, the 2 holes for it. This is the power transformer, which only has the 1 hole. This is the center tap of the high voltage winding. This is the high voltage winding that goes to the 5U4. And this, I would imagine, is the one that, I think it's filament. And this is the primary, which we've already established by the schematic I drew, that the variac goes here, so the voltage is varied when you turn the variac. And this is the 3rd wire. No, I'm sorry. The 3rd wire is up here, the red one, to the variac. These are the 3 wires for the variac. This is your primary of your power transformer, which I just showed you. And this is the 3rd wire of the variac, which is right here. The one with the red stripe. Apparently these other 2 wires are just plain white. So these 2 white wires are the ones for the primary of the power transformer, and that's where you're varying your voltage right there. There's your slider right there. So you got to be careful because the damn chassis fell down on top of this, and if it busts these windings, I'm done for. I'm done for. I've got I got another variac. I wish I could mount this thing on the chassis, but I can't. It's too big. So this is bad, having to run this like this. And it's got the slider here. And if I put that on a little piece of foam or something, well, this is going to rub into it, but if I do that, I put the knob on it, I can turn it, but I can't turn it now unless I put it into something so I can vary it. It's a real inconvenience not being able to operate this and have to keep turning the unit off all the time in order to adjust it and turn it back on. I think I'm going to take a break. My neck is killing me, just like it does at the computer, because I got to hunch over and get my face right on top of everything. So it's a little more comfortable in here. Anyways, we'll probably draw out some hen scratching here, and it's almost like, in my case, I got to remember everything, because I cannot draw out what I see here. In other words, I don't think it's possible to draw a schematic of something like this. I think we're going to end this video now. I scratched my head enough today. It's going to take a while. And I may not get the current out of this. I don't understand why. I'll tell you, it takes a Mr. Carlson to figure something like this out. It's a simple, I know I said it's a simple power supply. I'm just having a heck of a time trying to draw a schematic of it. Mainly because everything's so cramped in here, and I'm trying to see the wires, and my neck is killing me trying to get in here. and seeing where it's going, and then you got the polarity reversing switch, which is here, and that's making it extremely confusing. You know, with the polarity reversing, I really don't know how that can even be done, but it's done. You know, I don't need it, but I don't want to disable it. I got to make sure I understand this thing correctly, because if I disable it, then I got nothing. But I got to get this thing to have more current output. There's got to be a way of doing it, and the only way is that 150,000 ohm resistor, which is right here. Reducing that should increase the current. If that don't do it, I don't know how else you could increase the current. There's nothing else that limits the current in here. You've got a lot of high voltage going into that electrolytic from the 5U4, depending on where you set the variac. So you're getting the voltage going in, so when you're drawing current, your current obviously is going through the milliamp meter, and I have to figure it out, and because of this polarity reversing switch here, all these wires come in here, and it complicates things for me. So I really don't want to start snipping wires and doing away with the polarity reversing switch at this time. I know I said I want to. There's no point in it. It would make it easier for me to figure it out. Oh man, I wish I could get the schematic on this, but I've tried all over. I just cannot find it, because obviously they don't make it, and no idea when this was made. But anyways, I talked long enough. It'll probably be a while before I make any more videos on this, and I'm going by the number of views and likes on these videos, and if I see it dropping too much, I won't make any more videos on it and move on to other things. However, I will be working on this. I just won't be making videos of it. And when it is done, even if it limits the current, even if I only get 50 mils out of it, should be able to run most radios on that, except for a big radio. My main concern is trying to run these battery radios on it. It's not a switching power supply, thank goodness, because I didn't want that. So I should be able to get a noise-free DC power supply that will supply the radio. You can see that when I had the garage radio on this, it was drawing 12 mils, according to the meter here, and that 12 mils was pulling down this power supply, and I had to push in over 70 volts, 70-some volts, in order to get it to put out 53 volts onto the radio, and that wasn't enough. So it's similar to the ICO 950. It puts out the voltage, it just don't put the current out. And that's my dilemma, folks.